Hello, in this first video we are going to see solar geometry, which is the first element belonging to solar radiation, which is the first unit of our solar project. Previously, to understand our Solarcv project, which is based on HTF system and solar field, we need to understand solar radiation. Solar radiation is the set of electromagnetic waves which are emitted by the sun. In the sun represents over 99% of the solar system mass. Inside occurs some nuclear reactions where the mass disappears and energy is released to the surface. Here we can see that the energy is traveling through the space and it hits the surface of the Earth. However, how we are going to consider the sun for our purposes like a black body? A black body is a material, is a substance which is not able to reflect nothing. For example, if we have here a surface, a solar ray is traveling along the free space and it hits the surface, and it's not going to be any reflections, i.e. it's going to be here and then it's going to pass through the surface without reflection. For example, we can see here that this is our surface, for example the sun surface, and here occur the nuclear reactions and the energy is going to be released here, hit the sun surface, and it's not going to be any reflections. That is, it's going to travel through the surface, and here for example is the Earth. So how we are going to consider this black body behavior with the Plancks equation? However, it's too tedious and it's so hard to understand. So we can simplify this equation in the Stefan Boltzmann equation. It's simpler, and here we can see the energy, the Stefan Boltzmann constant, and the temperature of the surface, because the star really is very hot, because it's inside the temperature is over 2 million Kelvin degrees. However, we are going to consider the temperature of the surface, and it's over 6,000 Kelvin degrees. Air mass is another important concept, because this is equal to the actual path length through which the solar radiation must pass to reach the Earth's surface. Am is equal to 1 divided by cosine of phi. And now we can estimate very easily with a simple equation. We have a vertical post, for example, and here is the sun. This post has a vertical heat, and the sun is heating this post. So it's going to project a shadow of S length. Now we are going to have this, a triangle. And now we are going to have here an angle. Now, if we do the root square of 1 plus s divided by h, and this to the square, we are going to have an. For example, imagine that this is 1.5, this is going to be an 1.5, and this is the standard for photovoltaic cells. There is a special case, and this is air mass 0, and this is the air mass in the free space. Air mass 0 doesn't vary, and this is the total power density integrated over total spectrum, i.e. from 0 wavelength to infinite wavelength, and is known as solar constant. Solar constant really is the radiation which is in the Earth's surface, i.e. watts per meter square, and this is 1,300 watts per meter square. Here in this chart we are able to see the IRradiance, which is watts per meter square per wavelength, so really is watts per meter cubic in function of this wavelength. And for example, here we have a black body of 6000 Kelvin degrees, i.e. the Sun, and here AM 1.5, which is our standard. Now we need to understand another important concept, and this is, for example, Earth rotation and Earth revolution. For example, Earth rotation describes the rotation of the Earth around its axis and resulting in the phenomenon of 24 hours called day and night. If we have the face of the Earth toward the Sun, it's going to be day. If we have the face hidden to the Sun, it's going to be night. We have that a rotation is 360 degrees. So if we divide this value between 24 hours, we have that the sphere is really the Earth is going to rotate 15 degrees per each hour. Here we can see, for example, that the angular speed is going to be maximum at the equator, and there is not going to be no speed here in the poles. Earth revolution is another important concept because it's going to be very, very important for our purposes. Although in English the term revolution is the same, really Earth revolution and Earth rotation have very, very different concepts, because Earth revolution is the rotation, the revolution of the Earth around the Sun, and the period is 1 year, whilst an Earth revolution, an Earth rotation is 24 hours. Whilst Earth revolution generates stations, Earth rotation generates day and night. Here, for example, we can see that the plane around the Sun is not a circle, because if this plane were a circle, it could generate just a station, because you are going to be at the same radius around your center, and this is the Sun. However, we can see that here in the winter solstice, this phase of the Earth is at the largest length to the Sun. Here in the equinox, these phases are at the same distance, so the day and the night during the same. And here in summer, in the summer solstice, this phase is at the nearest distance, so we are going to have the largest day in the year. Now we have another important concept, and this is the inclination of the Earth axis, because really the Earth is not rotating like this. It's rotating with an axis, and this is very important, because really with the Earth revolution around the Sun, this is going to generate the stations. As we can see, in 21st of June is the summer solstice, and the North Pole has 23.5 degrees toward the Sun. On the other hand, we have that in 21st, 22nd of December, we have this winter solstice, and it's the opposite, because we have that the South Pole has 23.5 degrees toward the Sun. And finally, we have that on 23rd of September and 21st of March, we are going to have respectively the autumn equinox and spring equinox, because the circle of illumination, i.e. the circle which separates day and night in the Earth, is going to be the same. It's going to be across the main meridian. Here we can see that we have studied. Obviously, because the annual change in the relative position of the Earth axis in relationship to the Sun causes the different height in the Sun. So we are going to have different height of the Sun along the year. For example, if I am here in summer, we are going to see the Sun with a path like this, but in spring or in autumn, this path is going to be tilted, and in winter is going to be more tilted. So the sun path is going to be shorter, and the day is going to be shorter than for a day in summer. We have that the total variation in maximum solar altitude for any location on the Earth over 1 year is 47, because the Earth tilt 23.5 degrees, and because we have one semester and another semester, we're going to have 23.5 multiplied by 2, so 47 degrees. We can see perfectly this concept here. We have the north, the south, and for example, for the equator, the line which divides the Earth in two half parts, we have that this point, this line is for June solstice, summer solstice, and measured from the north is 66.5 degrees, and measured from the south is going to be 130.5 degrees. And in the opposite, we have the other angle for December solstice. The solar position is best to be defined with the polar coordinate system than Cartesian coordinate system, because it's better to define our position with a radius and sun angles. For example, we can see here that we have an horizontal plane, which is our main plane, the zenith, which is our above position, the nadir is the opposite from to the zenith, the north, the south, the west, and the east. And now, and here we are going to have the north-south line, west-east line, and here the main meridian. And we need to define some main parameters. For example, the zenith angle is very, very important, because it's the angle between the sun position and our vertical. Here is the observer, and we have this vertical, and this angle is the zenith angle. It's very important to take into account that if we have the sun directly above to us, this zenith angle is going to be 0, and if the sun is just in this main plane, this horizontal plane, i.e. is going to disappear, this zenith angle is 90 degrees. On the other hand, we have elevation angle or solar height, and this is the complementary angle with zenith angle, because zenith angle is this angular distance from this line, this vector, to this height, and elevation angle is the opposite, is from the horizontal line to this vector. And on the other hand is the same. If the sun is here, the angular distance is going to be 0, and if the sun is directly overhead, i.e. zenith angle is 0, the elevation angle is going to be 90, because they are complementary angles. We have clockwise angle. This is a little difficult to understand, because we have our north and south line, and the clockwise angle is the angle we need to move our sun to this north-south line, and this is going to be 180, i.e. p-radians, if the sun is here, because we need to measure this angular distance to the south, and if the sun is here, it's going to be minus 180, i.e. minus p-radians. Another angle is solar azimuth, and this is the opposite, is from north-south pole, from north-south line to the projection of the horizontal line, i.e. from this point to the observer. Now it's very important to take into account that we have a solar thermal power plant, and our mirrors need to receive the solar radiation. So we need to catch the best radiation as possible. So we need to take into account two main angles. The incidence angle is the angle between this normal vector and the vector of the solar ray. And now, because we need that this incidence angle is 0, because our main objective is that the solar ray hit with 0 degrees. So we are going to have a tracking system with 2 axes, or if we haven't got enough money, we are going to have just 1 axis. We need to follow throughout the day the sun with 1 axis, or if we have 2 axes, we are going to do this and this. In following units, we are going to study this more. Now we have a solar radiation received, and this is very important because we are going to have a spectrum of wavelength from 0 to infinite. But really, with the span of this wavelength, which is very, very important for us, is the visible spectrum and the ultraviolet, because we know that the speed light c is equal to wavelength multiplied by frequency, and we know by Plancks equation that the energy is equal to h, is the Planck constant, multiplied by the frequency. So if the speed light is a constant, for lower frequencies we are going to have higher wavelengths, and on the other hand we have that the energy is equal to h multiplied by f. If we have higher f, we are going to have higher energies, so we need lower wavelengths. For that reason, we are going to catch this visible spectrum and this ultraviolet spectrum. Now, as we saw, we have solar constant, and this is the result of integrate AM0, i.e. the air mass in the free space, and it doesn't vary. So solar constant is equal to 1,360 watts per meter square, and this is the irradiation, i.e. the radiation per meter square outside the atmosphere. Now we can see that we are receiving this solar constant, i.e. 1300 outside the atmosphere, but we are going to lose some energy from this atmosphere to the surface, because we are going to have the power plant on the Earth's surface. We are not going to have our plant in the space, so we are going to lose some energy because of the reflection in the atmosphere, the mountain, the oceans, and something like that. And now here we can see this perfectly. Here we have the solar constant outside the atmosphere, and we are going to lose some energy here. So really the effective energy that we are going to consider is over 970 watts per meter square, and we are going to approach this amount to 1000 watts per meter square, and this is the standard for photovoltaic cells and for our case for a solar thermal power plant. Now we have probably the main concept in this first element, and this is irradiance and irradiation. We have that these concepts are based on radiation, but they are not the same. Irradiance is the instant energy received per meter square, i.e. we have radiation, which is being transmitted from the sun to the earth, and we need a concept to consider this for a given area. And this is irradiance, is the amount of energy that we get for a given area, for example a meter square. And if we translate this instant energy to a given period, for example a year, we are going to have the irradiation. Irradiation means the amount of energy received for a given period of time for a definite area, for example in kilowatts hour per meter square per year. Here we can see perfectly this concept because we have the radiation, and here we are defining an irradiation because this area has, for example, a 2 meter square, 3 meter square. And if we translate this, for example, for a year, we are going to obtain the irradiation. And here, for example, the source Solarcv, we can see a map of China with the values of irradiance. Here, the red values represent higher irradiance. For example, although we are going to consider to the end of Solarcv project a thermal solar power plant, really we have different sources to consider this irradiance and irradiation concept. For example, with a performance of grid-connected photovoltaic system, although in this case, unless solar panels are used as an energy support for the solar thermal power plant, this application is not going to be useful. If this plant were a thermoelectric plant, we could apply this source, although it's not going to be useful for our purposes, although it's very, very useful to understand this. Here we can see the average daily electricity production for the given system in kilowatts hour. EM, this is the same. HT is the average daily zone of global irradiation, and some concepts that they would be able to understand. Now we have a part of irradiation and irradiance concept. We have other very important concepts like direct radiation, diffuse radiation, and reflected radiation. We have that from the space, from the sun, we are going to receive some energy, although this total energy is not going to be absorbed by the Earth's surface, but we are going to lose some energy because of the reflection on the clouds, because of the absorption of the mountains, for example, because of the scattering on the dust particles on the sky. So we can define 6 types of different radiations. Direct irradiation is the solar radiation that reaches a certain area without having undergone any change in its direction, i.e. we are going to receive this in the atmosphere and it's going to pass through the atmosphere without changing its direction, and it's going to hit directly this surface. Another concept is direct normal irradiation, DNI, which is the direct irradiation measured on a surface perpendicular to the direction in which the sun's rays are received, i.e. we are going to have here a surface, our mirror, and the solar ray is going to hit with 0 degrees. And this irradiation is measured with a peer heliometer. It's mounted with 2 axes because its purpose is going to follow throughout the day the sun. On the other hand, we have other irradiation concepts like diffuse irradiation. Diffuse irradiation is another important concept because it's the part of the radiation that is reflected and absorbed in the dust particles, gaseous, mountains, etc. And it hasn't got any defined trajectories. We can have the diffuse irradiation in wherever direction. Now we have reflected irradiation, and any material which is in the space is going to be a reflection coefficient. And for example, for a perfect mirror, if a solar ray hits this mirror, if this mirror has a 100% of reflection, the same energy is going to be reflected. So for example, if we have 1,300 watts per meter square in the Earth atmosphere, and there are some reflection on the atmosphere, we are going to lose this reflection because we are just considering this direct irradiation. Global irradiation is made up by direct, diffuse, and reflected irradiation, and this is measured with a pyranometer. Here we can see 2 pyranometers. Finally, we need to understand that it's very important to consider the type of technology used. The main objective is determining the amount of that irradiation for a given area, because we are going to have our solar thermal power plant, and we need to know perfectly for each moment how much energy we are receiving from the space, from the sky. With the standard AM 1.5, which is the standard air mass for photovoltaic cells and for our purpose, with clear skies, i.e. without clouds, we are going to have a diffuse component about 10%. We mustn't think about we are not going to have any diffuse component if there aren't any clouds. We are going to have always diffuse component because of the dust particles, gaseous molecules, and something like that. Finally, we have that a great irradiation application is the elaboration of graphs where global, diffuse, and local radiation are plotted to determine the peaks and hours. Peaks and hours is a very important factor, and this is the power density integrated throughout the day, converted into equivalent number of hours at solar noon intensity, i.e. we define that solar noon intensity is over 1,000 watts per meter square. So, for example, a day we receive 5,000 watts per meter square. So we can translate this into 5 peak sun hours, because we divide this total irradiation received divided between the standard, and this is 1,000 watts per meter square. Now we have that solar angles variation throughout the day, because for example, for northern hemisphere, here we are living in Madrid, in Spain, and this project, this Solarcv, is for Italian, Greek, and Spanish people. So the plot, the picture is like this. We are going to have that the Earth axis is 23.5 degrees. So this angle is going to be positive in June solstice, it's going to be negative for December solstice, and it's going to be 0 for both equinox, i.e. for March, spring equinox, and September equinox, i.e. autumn equinox. So the day and the night are going to be the same, they are going to last the same hours. Although with the concept of irradiation and irradiance, the different irradiation components, we need to understand in this element of this unit that a solar ray carries the same energy along all year. So if a solar ray carries, for example, 900 watts, this solar ray is going to carry the same energy for the solstice in summer and the winter solstice. The difference is the incidence angle, because in June we are going to have here the sun, and the surface, for example, for this case, is going to be 1.04 meters square, whilst for the winter solstice we are going to have this square. It's going to be higher. In winter the surface is higher than for summer, so the first number of the fraction, the ratio, is the same, but the second number is higher in winter, so the irradiation is lower, and we are colder in winter than in summer. Here, for example, you can see this concept. We have 900 watts and 900 watts, but the surface in summer solstice is the lowest along the year, and for a winter solstice the surface is the highest as possible. So in this video we have seen these concepts. We must realize about the incidence angle and irradiation and irradiant concepts. We know that for the north hemisphere case, in winter the solar rays are more distributed than in summer, and in the south hemisphere is the opposite. That if the Earth's surface could be tilted, the radiation was received perpendicularly, i.e. for a very good solar thermal power plant, we need tracking system to follow the sun throughout the day with 2 axes or 1 axis. It depends on our money.